All right, guys, let's get started. So today we're going to switch gears and start talking about how to find vulnerabilities. So I guess one bit of administrative before we dive into this paper. Hopefully this is not a surprise to anyone. We have a quiz on Thursday in lecture. So instead of lecture, you'll have 80 minutes to fill out a quiz piece of paper on Thursday. Hopefully that's sort of expected. But if you have any problems, send us email. All right. So the topic of this lecture is going to be all about how to find vulnerabilities in contrast to many of the things we've been talking about so far, which are about how to mitigate and deal with vulnerabilities. So most of the papers we've been reading so far in this class have been taking the mindset of bugs are bad, that's where the exploitable vulnerabilities lie, but we're going to design the system so as to minimize the effect of those bugs, or maybe redesign it so there's fewer bugs, etc. But the focus of this paper is really squarely on actually finding and hopefully preventing those vulnerabilities in our software. And this is in general a pretty fruitful plan, even though we don't talk about it very much in this class. But in general, people worry a lot about exploits and what kinds of software bugs might lead to exploits. There's a fairly widely used database called CVE, Common Vulnerabilities and Exposures Database, ran by large organization that tries to categorize actually all kinds of bugs in software so that people can understand whether their software has some exploitable bug or not. And in general, many companies have bug bounty programs that try to incentivize various security researchers or developers in reporting any security vulnerabilities they find to those companies. So people care a lot about finding exploitable bugs. And what we're going to talk about today is how do we automate this process? How do we more systematically approach this problem of finding exploitable vulnerabilities? And roughly, this paper takes a little bit of a step back and says, well, we're just going to think exploits are really a subset of all bugs. And this paper in particular isn't super necessarily concerned whether a particular bug is exploitable in the sense of what you guys did in lab 1 of actually triggering a buffer overflow and injecting code and all that stuff. What they want to know is there a bug? And the mindset this paper argues for is that pretty much any bug you might have in your software could be exploitable, so it's better to fix it. And good to fix it for all kinds of reasons. So this is what this paper is talking about, but there's lots of ways to systematically find bugs. We'll talk about them in a bit, right? You could just do testing manually. There's a pretty popular technique we'll talk about called fuzzing. And what this paper proposes, this idea of symbolic execution, is sort of on the extreme end of the spectrum going from manual testing to more sophisticated symbolic execution, and this is what Lab 3 is about. If you guys haven't started Lab 3, which, maybe you haven't, Lab 3 is all about having you guys build a little symbolic execution system for Python code you've been poking at so far. Make sense? So that's sort of the landscape where this paper is trying to fit in, trying to find all kinds of bugs, and hopefully they'll include exploitable bugs. If you fix them all, then our software is going to be more secure. Make sense? Questions at a high level? All right. So what does it mean to find bugs? So how do we go about this? So loosely speaking, right, so we have some piece of code that we want to analyze. And somewhere in our code, maybe there's a bug. And our goal is to figure out, can we actually get this bug to cause a problem for us? And pretty much any plan is going to revolve around trying to provide inputs to this program. So maybe here's input 1. You give it to this code, and the code runs along, executes some code, and it doesn't hit a bug. Okay, so at least this bug isn't always there, but maybe there's other inputs that do trigger this bug. So you provide that input and run the code again, and this time, you run it and you hit the bug. Okay, good. So hopefully you'll be able to determine that something bad happened, and that's a bug worth fixing. But in order for this, well, this is a super simplified picture. We'll dive into the details of what this means shortly. But in order to make this picture fly, you need a couple of things already. So one is you need to know that you actually hit the bug. how do you know that something bad happened? You're going to run this program, you're going to give it an input, it's going to run. There's not a light necessarily that lights up saying there's a bug. Some things are pretty obvious, like maybe the program crashes. That's probably always a bug. But maybe something bad happened but you didn't notice. You got to know that you've actually hit a bug. So the first and actually most important aspect of having a plan to find bugs is actually to define what does a bug looks like. So we need to pin down what does it mean for our program to have hit a bug so that we know when we found it. And we'll look at some examples in a bit. The other part that you need in order to look for bugs in your software is to have some plan for what inputs you're going to consider. And hopefully some of those inputs are going to trigger your definition of a bug. So you need to check a bunch of inputs in some way or another and then see if any of them trigger your definition of a bug when you run your application on it. Make sense? Really clear. Any questions so far? Feel free to ask a question through Kevin as well. All right. So let's talk about these two different categories. So there's not there's not a huge amount of interesting stuff to say about defining bugs, but we'll sort of lay out at least some rules or some plans for that. And then most of the action is really in figuring out what inputs are worth checking, because that tends to be where a lot of the trickiness is. How do you construct an input that actually triggers a bug? But let's first dive into this question of how do you actually define what's a bug? So how do you know you've hit a bug in your program? Any thoughts? Yeah? Yeah, okay, crash. Yeah, that seems like a pretty great plan, yeah. So your program should probably never crash, and as you've learned in Lab 1, crashes can be for reasons that might be exploitable. So yeah, crashes are almost always not a good thing to have. Other problems that might be worth catching? Yeah? Oh, yeah, good. Yeah, so maybe, okay, so crash is a kind of a general plan. Like, okay, this should never be like any program. You don't even have to know what the program is. If it crashes, I can tell you it's bad. But then you could have really sort of app-specific things. In contrast to here, crashes, these are sort of, we'll say, generic definitions of a bug that almost always work. Other is maybe, yeah, sort of, there should be an unreachable function. And this could be some actual function in your code that should never be called, although it's a little bit funny there. Like, why is it in the code if you expect it to never actually run? Maybe just remove it and then you'll save yourself the trouble. But the point still stands. Like, there could be invariants about your application that make sense. So a pretty common example of an unreachable function is used to encode application-specific rules in the form of assertions. So assert X, you might actually write assert X in your code, and what this means is really this translates into basically if not X, then panic. And this panic should never be reachable. It's kind of like a crash, but it might not actually crash the code. You might actually compile the code for production use. You might actually remove these asserts so they don't take up code, don't take up time at runtime. But many applications have assertions in them for debugging purposes, and they're probably good definitions of a bug as well. Yeah. Other thoughts? What might be good examples of bugs to look for? Yeah. Yeah, okay, so divide by zero. Yeah, divide by zero. Certainly the paper worries a lot about that. I guess it's a subset of crash bugs, but indeed, probably not a great thing to happen, although, divide by zero is probably in bugs that are maybe not so exploitable. Or depends, right? Like, yeah, maybe you start digging and you realize, it's not just a divide by zero, there's more bad stuff going on. But just the divide by zero probably isn't directly exploitable. You might worry about denial of service attacks, but it's not code injection. Another example of something that might not be quite a crash, but sort of out of bounds memory accesses. So it might not be a crash, you just went past the end of an array, but it didn't crash, there's something else there. Very much like in Lab 1, you don't always crash. But if you can catch that, that's almost certainly a bug that might be actually in the exploitable category, even if it's not a crash. So this paper adds all these checks as well for out-of-bound memory accesses. You can sort of think of it as like the same stuff that Baggy was trying to look for at runtime. These guys want to look for many of the same category, or at least for this category, the same category of bugs at analysis time. Make sense? And on the sort of application-specific side, right, you could sort of, sky's the limit in terms of what you could write. So you could imagine, if it's a bank application like Zubar, maybe you would say something like, oh, the sum of all the accounts is a constant. There should be never sort of money being made up in the system. Doesn't matter what happened. Or maybe if you have some system where each user has their own data, then maybe an assertion is like X's data accessed by Y. So by Y meaning like a request came in from user Y, but it somehow ended up touching X's data, etc. And you could write all kinds of application-specific assertions, but here you really have to know the application, understand what is a bad thing in the context of that app. Make sense? So these things end up being pretty similar across the board for all these techniques of testing, fuzzing, symbolic execution. So we're not going to spend a whole lot of time talking about these assertions. As I mentioned, much of the action ends up being in sort of this input enumeration part of the bug finding plan. Make sense? Questions so far? Yeah. Infinite loops? Yeah, that's an interesting question. So, it's sort of maybe closer to a divide by zero in terms of like what happens. The application just locks up. One possibility might be, you could say, excessive resource use. And so here, maybe it could be loops or memory allocation. It sort of depends on the context of what you're building, but for example, if you recall the Firecracker people, the AWS Lambda service, they worried a lot about resource use by every VM. And actually one of the bugs that was discovered in Firecracker was that they didn't bound the memory allocation for a buffer for the serial port in their virtual machine. So yeah, that might be, like if you care about that, then maybe this is a bug condition you could say. Like regardless of what you're testing, if the application ever uses a gigabyte of memory, it's probably too much. So catch that. And similarly, like if you ever use more than, a second of CPU time, it's probably a lot. So worth looking into. It might be a false alarm. For many of these things, right, these are not necessarily, there might be false positives. It might be that, you find something and then you realize, well, for this weird reason, that's actually okay. But anyway, these are what the tool is going to find for you. And then it's up to you to decide if you care. Yeah, good point. Any other questions? All right. So let's try to now talk about different ways we might be enumerating inputs in our program. So the first thing that's worth talking about, just to set the baseline, is manual testing. So probably pretty familiar with just manual testing. So you write test cases, and the test cases, kind of interestingly, it's a combination of both of the things we've talked about here. So a test case typically has both an input that you describe. Here's what you feed into your program in order to test it, plus you actually probably just write down the expected behavior, outcome of some sort. So the nice thing about manual tests is that you're actually able to have sometimes very precise control over what is a bug. So precisely specify bugs in different scenarios. So you might not write down a fully general plan, like if this happens, it's always a bug, but you could write down fairly specific things like, for this specific input, that would be a bug. Don't let that happen. So in some ways, manual testing lets you get at more interesting properties sometimes than you would be able to do with a cross-cutting plan that requires writing a universal sort of bug definition. Another nice thing about manual testing, of course, is that it's probably pretty effective to use manual tests for regression testing. So what I mean by regression testing is if you find a bug in your code, you should fix the bug, but you should also write a test that would have caught the bug so that if you ever reintroduce the bug by accident in some form, that test will fire again, and you'll notice. So tests are a great idea, so I'm not saying you shouldn't write tests, and in fact there's some really nice thing about tests that you can get. But from our perspective of wanting to catch security vulnerabilities, tests are not entirely satisfactory. So tests really get at, or manual written tests, get at bugs that the developer was thinking about. So if they're thinking about writing a test, they probably were thinking about that special case in their code, and maybe they handled it correctly. And what we really want to find in many of these security vulnerabilities is cases that the developer didn't realize they have to handle correctly, or sort of subtle situations. So one way to maybe characterize this is that for manual testing, we have actually relatively few inputs that we're going to synthesize. Compared to what we're going to do with fuzzing and symbolic execution, manual testing, you're only going to write a huge number of test cases by hand. And as a result, the coverage that you get, meaning what fraction of the code gets executed by your tests, might not be actually very high. So there might be bugs hiding in code that you never ran in any test case at all. So that's one bummer. With manual tests, and sort of going hand in hand, is that you might actually miss some corner cases, because the developer has to be clever enough to cook up a test case. And if there's something they're not realizing, like, oh man, this could be a negative number, or this could be 0, or the adversary could supply a really big value here, if they're not thinking about that in the code, they might not also think about it in the test cases they write. So that's one downside of sort of tests. And maybe the last thing I'll mention in this category is these things are pretty high effort. Takes a while to manually think and write all these test cases, and might not always happen. So, good plan. And I should say, pretty much every serious software project these days does testing, does fuzzing. Many serious systems do symbolic execution these days, although that's maybe slightly more fancy. But certainly, like Microsoft runs symbolic execution on Windows and finds bugs all the time using symbolic execution techniques, and widely used in a bunch of other places as well. So they're all sort of important approaches to finding bugs, and they all have their own sort of strengths and weaknesses. All right, so make sense about manual testing? What's good, bad? Any questions? All right, so let's talk about the next plan, which is this idea of fuzzing. I want to describe this mostly for two reasons. One is it's really important in practice. So in practice, fuzzing is really widely used because it's easy to use and effective, finds lots of bugs. And the paper didn't describe it because, well, the paper is about symbolic execution. So important for you guys to know what fuzzing does or how it works to some extent. So fuzzing is this idea of basically providing random inputs. So here we have our code that we want to run, and we've already figured out some plan for what's a bug. And in order to figure out if our code can hit a bug, we're just going to generate random inputs, roughly speaking. So generate some random bytes, feed it into the code, and off we go. And probably it's going to not do anything interesting. Then we'll do it again and again and again, many, many times. Use a lot of CPU time to try lots of random inputs. And one really nice benefit of providing random inputs is, of course, you get lots of inputs because they're cheap to generate. You just let your computer generate many inputs, and you don't have to think very hard yourself. Relatedly, because the computer is just generating random inputs, it's often actually surprisingly good at finding corner cases. So the random generator doesn't really have a preconceived notion of what inputs should look like. It'll just try all kinds of random things, and maybe it'll trip up your code in ways that your code wasn't expecting as an input. So these are sort of nice things. I guess another nice thing about fuzzing is that works on a black box system. What I mean by black box system is that you don't actually have to look inside. You just treat the whole system you want to test as some abstract thing, and you're just going to feed inputs to it and decide if it hit a bug by your previous definition. You don't actually have to compile it in some special way. You don't have to really look at its source code necessarily. All you have to do is be able to run it on some input. So it's a really nice plan. Of course, one downside of fuzzing is that, well, I guess one sort of mechanically downside is that there's a lot of CPU usage. So you need a lot of CPU to try lots of random inputs. And sort of colloquially speaking, this fuzzing thing, one limitation is it's kind of stupid. Like, it just tries random things. It doesn't really know what inputs to feed in order to get the program to explore interesting cases that are likely to lead to bugs. So there's two interesting techniques that I'll tell you about that people apply to fuzzing to make it more likely to find useful inputs. But before we dive in, any questions? Does sort of make sense as a bug finding strategy? Sort of feeding random inputs at a high level? So there's two tricks that people generally use with fuzzing. One is this idea of using a generator. So I guess the downside, maybe to formalize this, is stupid. Downside, maybe we'll describe it as having weak coverage, meaning that you might not actually get to execute a lot of the code by just providing blindly random inputs to the program. So one idea in order to improve this situation is to use what's called a generator. So instead of just blindly jamming random bytes in the input of this program or a function, what we're going to do is actually the developer is going to write a generator which takes some randomness in as input and then produces a more plausible looking output. So for example, if you have an HTTP server, instead of just blasting it with random bytes on the network, what you might do is you might write a generator that formulates reasonable looking requests. So it'll always say get, and then here's a random thing, and then it'll have a header. Here's like a random header value, colon, space. Here's another random thing, and then maybe a couple more. Then you have your new lines, and that's it. So the generator sort of encodes some knowledge that the developer has about what legitimate inputs should look like. So if you're just sending random packets to a web server, most of those aren't even legit packets. They'll get discarded super early, and you'll never trigger any interesting code downstream. But by writing a generator, you can help it along by basically writing enough structure in your generated inputs to get past some initial sanity checking in the server and let it explore some other parts of the code. Make sense? So this idea of generative fuzzing is pretty widely used. So oftentimes when people say they're trying to fuzz their application, a lot of what they talk about is trying to figure out what is a good generator. So instead of blasting random inputs, you try to figure out, well, I want to generate a bunch of requests that look like legit HTTP requests. Maybe once I exhaust all that and nothing seems to be finding interesting bugs anymore, maybe I'll write a different generator that knows even more and drills down into a subspace or a part of kinds of HTTP requests that are interesting to my application and so on. So a lot of what ends up being where you spend the effort is writing generators if you want to do fuzz testing. That sort of reflects a class of inputs that you want to really explore thoroughly in a randomized way. Make sense? So generative fuzzing turns out to be pretty good. And the other technique is to guide the randomness in some way. And this is typically in the context of coverage-guided fuzzing. So in coverage-guided fuzzing, the idea is to not start with a completely fresh random input every time, but instead to slowly randomize the input and hopefully get it to find more interesting code paths to explore. So again, the plan is we'll have our code, and here's some input that we want to provide. And what we need in order to make this coverage-guided fuzzing work is we need some kind of feedback from the code to tell us whether we actually hit something interesting or not. And oftentimes what ends up being useful is having the code output some kind of coverage information. By coverage, I mean some description of which functions were actually executed or which lines of code were hit by running this input. So once we have this coverage information, what we're going to do is we're not going to consider completely random inputs every time. Instead, we're going to have some set of interesting inputs to consider. This is typically called a corpus of different inputs. So here they are, a couple of them here. And every time we want to run the code, we're going to pick one of these things from the corpus. And the corpus represents inputs that trigger all kinds of different parts of the code. So hopefully the corpus has a bunch of different looking inputs that, taken together, explore a good chunk of your application's lines of code. So we're going to pick some input from the corpus, and we're going to mutate it a little bit. So the mutation, the idea is that this mutation is random, but we're going to either add 1 byte, remove 1 byte, flip 1 byte, very small changes to the input, and then we're going to feed it into the code, and then we're going to run it and see what the coverage was. Now, of course, one exciting outcome could be that, oh, we have found a bug. That's just fantastic. Rarely happens with fuzzing, just because we're trying so many different inputs. But if we find a bug, great, we can report it. If we don't find a bug, what we do is we look at the coverage, and we see if the coverage is significantly different from the coverage we already had, then we can actually add the input after mutation back in. So we can add it if there's new coverage. So this way, we can keep generating various inputs that hit different parts of the code, and if we mutate the input and it doesn't hit any new lines of code, we'll just forget about it. We'll try mutating it some other way. And the idea of this coverage-guided fuzzing is that it'll nudge us to really consider inputs that poke at different parts of our program, and hopefully, in that way, improve the coverage. And in practice, this works pretty well. There's a super popular tool called AFL Fuzz that implements this coverage-guided fuzzing. It's been used by many people to find bugs and security vulnerabilities in lots and lots of software. One reason why it works well is partly because it's black box. It's easy to apply it, and it's pretty fast and has some good heuristics for how to evolve inputs and how to monitor coverage. Okay, make sense? Question? So one way, okay, so why do we add the input back to the corpus? So one way to think of it is we have some piece of code and there's an interesting if statement, like it checks, do we even have a legit HTTP request in our web server? And most random inputs don't pass that check. They're not legit. They don't start with get. But then, maybe by chance, we'll generate a thing that starts with get. Well, if it gets us past that if statement, we should remember it and start from there next time, because it took us a while to get past that if statement. And once we've gotten past it, we should start from that and evolve it a little bit further, and maybe it'll get us even further down in our code base, instead of sort of trying to guess a valid-looking HTTP request every time from scratch. If we try to guess it from scratch, the probability of getting an interesting input every single time is tiny. But if we remember the interesting sort of basis vectors, if you will, then you can start from any one of them. It already gets you past a bunch of if statements. And then we can start from there and maybe get past one more if statement or get executing some other piece of code. So that hopefully gives you some intuition for why this works out well. Make sense? Other questions? Yeah. Yeah, okay, so the question is, okay, how do you bootstrap this? Well, you start with empty. Where does it come from? So, depends a lot. A pretty common practice is you ask the developer to cook up a bunch of valid inputs. Like, you cook up a bunch of legit HTTP requests and you dump them in here. Or if you're fuzzing an image library, like what the RLBox guys might do, for example, in Firefox, they might just get a bunch of JPEG images and dump them in here. These are legit images. Let's try to, mutate the legit images and go from there. So it's pretty common to seed the corpus with a bunch of legit inputs. That's usually not a huge imposition on the developer, and you still end up generating tons and tons of variations of them with lots of inputs. Oh, yeah. Question? How is coverage measured? So coverage, as I mentioned, so here, it's probably not... The important thing here, what we want to measure is what parts of the code are executed, and you can think of this loosely as which lines of code were executed while running this input. Sometimes you can think of coverage as a percentage, like, this particular input executed 30% of my lines of code. That's not a terribly useful thing here. What we care about is which specific lines of code were hit by running this input, and we remember this information for all the other parts of our corpus, for example, or for the initial input, for example. And then if the mutated input hits a new line of code that wasn't previously executed by any one of the things in the corpus, then we're going to get excited because, this input triggers more code. Let's save it so that next time we can start with that, and maybe it'll get us further in our execution paths. Make sense? Question? So, depends a lot on the fuzzer, and there's a lot of heuristics about how to make this fly. I think either one of those could be interesting depending on what kinds of bugs and what kind of program you're looking at. You can probably think of it as a baseline. Whenever you hit a new line of code, let's add it in. That's a sort of a fairly crude, but probably pretty effective metric. Yeah. Online question? How much slower are dynamic versus static tools? It's like comparing apples and oranges, man. So dynamic tools are something the developer sees. So the developer has to run this dynamic tool, and they're going to have to wait for the fuzzer or the symbolic execution system on their computer to give them some output, then they'll fix the bug, etc. Runtime tools are things that slow down the end user's computer. So things like baggy bounds checking are going to impose an overhead on the computer that's actually running this application in production. So you really have to sort of look at, well, in practice you probably do both, just because they often address different kinds of bugs or have different benefits. But the kinds of overheads we might be talking about here are things that the developer faces, like the developer's machine has to run lots of inputs, or the developer machine is going to have to run symbolic execution. Runtime overheads like baggy are really a different kind of an animal because the end user gets to suffer. Yeah, question?
So is this only useful for finding like classes, or is this specific to things? I know symbolic execution in general is practice.
Yeah, no. I think in EXE you can write any kind of assertion you want. So it doesn't have to be a crash. So a super important thing they find that's not a crash is out-of-bound memory accesses. Those don't crash them, but they find them anyway. That's super important, of course, because for C code, buffer overflows are bad. But EXE also supports any assertion you want to write. So if you want to write some assertion like this function should never be called, or the sum of the balances in my bank account should always be the same, you could write this, and EXE will try to find counterexamples that'll break your assertion.
Well,
Okay, so the question is if there's nonlinearities in your expression. Yeah, I think it deals with it all right. We'll look at some examples maybe later on, but nonlinearities don't really trip it up. Control flow is the big thing it worries about, but they don't actually fork on nonlinear algebra. Yeah. Question? So what are we actually testing? In practice, symbolic execution has been used for all of the above. So there's actually a symbolic execution system that can take a whole x86 VM and run it symbolically. So you can literally send it packets, and the whole operating system will symbolically run, if need be, if the packet is symbolic. But in the context of EXE itself, they really look at a whole process. That's the boundary. And then the developer marks something symbolic. It doesn't have to be the network input. In fact, they don't really have a plan for any interaction with the outside world. They don't really have a plan for syscalls. You're just going to run just code and don't make any syscalls, don't read, don't write. So it's up to the developer to have this make symbolic invocation somewhere that says, maybe the HTTP input, that's symbolic, and then go from there and run everything from that point onwards. So EXE relies on the developer to pin down where the adversarial input would be coming from by marking it as symbolic. Other questions? All right. So this is fuzzing, super effective in practice, but one downside still is that it really relies on getting lucky to sort of find the right randomness to hit some interesting paths in our code. And doesn't always happen, especially if you have complicated constraints, like maybe your input packet has to have a checksum, and randomness is going to have a hard time computing a valid checksum on a packet. So this is where symbolic execution comes in. execution. So symbolic execution is going to really try to help us have a more systematic plan for more reliably finding inputs that are going to trigger different control flow paths. I guess we could sort of, cover different execution paths of our application. And the implicit sort of assumption running under all of this is that if we can at least run all the code in your application, well, we might actually hit some of the bugs in that code. And if we never run it, definitely not going to find the bugs there. It's not a guarantee necessarily, for various reasons we'll talk about in terms of limitations, but pretty good plan to try to hit all the code in your application and see if you can make it crash. So there's a couple of cool ideas in symbolic execution in this paper that make it fly. We'll sort of unpack them in a second, but roughly the first plan is this pretty weird notion that instead of running on concrete values like actual bits like 0 and 1, we're going to have symbolic values in our code. And we'll look at some examples in a second that describe, that sort of hopefully clarify what it means to run on a symbolic value instead of a concrete value. And then, on top of having symbolic values, we're going to explore all possible paths instead of just one. So if we have an if statement in our code or some other branching, a loop, whatever, if we have some place in the code where we can run multiple ways because of an if statement or what have you, we're going to try both in exe if both are possible, instead of having to run the program many times and try to cook up inputs that actually hit each path. So we're going to somehow branch on all these possible control flow points. And then the last idea is to use what they call a SAT solver to actually decide what's possible. All right, so hopefully some of this is sounding familiar from the paper. So maybe let's first look into this somewhat surprising idea of having a program run on symbolic values. So here's just as a toy example, you might have some code, int x equals 5, and then we'll have a variable y, and this thing is going to be symbolic. So instead of being 5, we'll call the value alpha. It's like not a bit at all. It's not an integer. It's an alpha. Could be anything, so as far as we care so far. And then we might keep on, say z equals y times 2. And then we might write something like assert that 10x is never equal to z. So what this looks like is if 10 times x is equal to z, then panic. Very much like what we were talking about up there. You might write assertion statements that unpack to just an if statement. So the question is, can we ever hit a panic? Can this program hit a bug? And the idea is that we're going to run this with this alpha value, and the sort of underlying intuition is, maybe y is the value that the adversary gets to supply. So we don't want to specify exactly what this is. We want to reason about all the possible things that could happen if the adversary plugs in something for y. So this alpha is what happens if in exe you call make symbolic of pointer y. You get y being this alpha. And when we execute this code, what's going on is that we have memory locations for all of our variables, x, y, and z, and what's stored in them is going to be different, right? So x is going to be really a value 5. But then when we store alpha into y, well, we're really going to store some representation of alpha. So there's going to be a memory location, but we're going to, on the side, remember that, this thing isn't a real thing, it's an alpha, and we'll deal with it specially. And then when we have expressions like z equals y times 2, when we fish out alpha out of this location, we're going to compute on it symbolically as well. So when we compute y times 2, we're going to get 2 alpha instead of alpha. So then z is going to store 2 alpha. It's kind of a weird, just mathematical expression for what that value should be, instead of some bit level, what they call a concrete value. And then, if we get to this if statement, we can ask this SAT solver to solve this thing for us. So SAT solver is able to take expressions that involve both symbolic things and concrete values, and then tell us, is this a possible outcome? And if so, how do you get there? Or maybe it says it's not possible. Make sense? Questions? Yeah, question. Yeah. Yeah, so okay, it's not a magic box. Okay, your question is, well, what if you compute a SHA-1 of something in this if statement? Well, the SAT solver is probably not going to give you an answer. And what the paper talks about is you time out. So the SAT solver times out, and then you have to deal with it. So it's not going to be a complete oracle of every question you have in life, but something is going to be able to answer for you. So I can actually demo this for you. You guys have this SAT solver installed in your virtual machines. So I borrowed Richard's laptop, and unfortunately he went to sleep. Sorry. You might learn the number of characters in his password. That's a long password. Thanks. Sorry about that. So here in your VM, I'm just in the Python shell, and I can actually import the Z3 library. And Z3 is a SAT solver, kind of like the STP thing these guys are using in their paper. Just STP turns out to not be super fast anymore compared to Z3. The Z3 is sort of one of the fancier SAT solvers you can use these days. And we can actually cook up the example we have on the board there. So we can have A. We can say, oh, well, let's call that a Z3, maybe an int called A. And B is going to be, actually, I don't need a B. I'll just have a question to Z3, like, can we have 10 times x is 5, is equal to Z, which is 2 times A? And the answer is yeah. I can just set A to be 25, and it'll solve that. That's like a pretty cool tool. We'll use this as we go through various other examples here. But it's able to, like, that's a super simple constraint for it. But we can also give it more interesting constraints, and it'll sometimes solve them, or sometimes not. Make sense? Questions? All right. Yeah. So your question is, okay, so what can Z3 do and what can it not do? Sorry? It's really difficult for me to give a high-level overview of how it functions in this lecture. So it has you can sort of think of it as, it has a whole bunch of tricks, or for some kinds of statements, it has just decision procedures. It knows how to solve arithmetic. Like that probably didn't have to guess anything. It just knows some rules for how to manipulate integers. And for other theories that it knows about, like actually Z3 can even do strings and bit vectors and all kinds of funny, like you can do symbolic regular expressions. It's pretty crazy. It just has a bunch of heuristics that the developers of Z3 programmed into it, and some rules for how to massage constraints and what tricks to play. And hopefully these tricks work out and will give you some answer. It generally doesn't do exhaustive enumeration of values. By and large, it tries to use these tricks for really small things like 8-bit integers. Maybe you can brute force them. But it's a bunch of tricks, yeah. And it's really, these are fantastically effective. Like many things you might throw at it and you think, how the hell did it solve this? But yeah, there's just a lot of work. It's a gigantic piece of software, owing partly because it has a whole bunch of tricks in it that are coded in. And works pretty well. In general, the kinds of things you can give to Z3 are satisfiability constraints, and they're NP-complete, so can't possibly solve them. Whatever. It's not a theory class, so we're not going to concern ourselves with P and P. But that's a hard problem, and it doesn't solve that efficiently in every single case. But it's just been super optimized for all kinds of program analysis type queries. So that's maybe the sort of right mental model to have for the purpose of this class. And hopefully it's also correct, although to some extent maybe you can check the answers, at least if it gives you an assignment. Sometimes it can actually say no. It's like if we give it another formula, like say, can we have 10 times 5 equals 3a? It says no solution. That actually says, at least as far as Z3 knows, there's no way to solve it. That's not a timeout. It's not a doesn't know. It just tells you there's no way to pick an A that'll make that formula true. And other times, I actually had a hard time cooking up a thing that it times out on, but sometimes, like the example of SHA-1, it'll probably struggle a lot and eventually time out. Or maybe never time out. Maybe it'll just keep running however long you want, but never giving you anything useful. All right. Any other questions about sort of what symbolic values look like? So one thing I wanted to look at is to look at sort of the overall structure of what exe looks like, and then poke at an example that's maybe a little bit more interesting than the example over there, and see how exe would go about running it. So what does exe look like? So you start with some C program that you want to analyze, and then in their implementation, they feed the whole thing through a translator that takes your code and outputs more C code. But what happens in this translation is that they add a bunch of things. So one thing they add is they add all kinds of assertions to catch bugs. So whenever you access an array with some index, or you do a pointer operation, they're going to add some code to implement this sort of bug definition that they have baked in. That could be a combination of some generic things, or if you, as a developer, already wrote an assert, well, they're going to maintain that assert in the code. And in addition to defining bugs, they're going to implement symbolic execution, which means they'll instrument all the operations. So things like expressions, or assignments, or control flow, like an if statement, etc. So if they see an if statement in your C code, they'll output other C code that checks if that if statement is branching on some symbolic value. And if so, do something fancy. If you're doing an expression like 2 times alpha on our example over there on the right, they're going to output C code that's going to check, is the thing we're multiplying by 2 a symbolic thing? If so, do one thing. Otherwise, just multiply the constant by 2. So they're going to really augment the C code with lots of extra information or lots of extra logic to operate on symbolic values. And then they are going to run this in a Linux process. And this process is going to maintain in memory an actual, usual memory locations you might have in a C program. But then they have some kind of a table on the side that overrides certain memory locations and says, this memory location, so you might have variables X or Y or Z might be this whole array, who knows what. And on the side, they have a table that says, this Y value, you thought it's just a 32-bit memory location. Actually, think of it as containing an alpha. But X might be 3. And then this array Z, maybe elements 0 and 1 are values 0 and 1, but then you have a beta and then 5 alpha, whatever. I'm just making up some examples. But they maintain enough data structures to basically pretend like you have a memory consisting of either concrete values or symbolic expressions. And then whenever you're operating on them, they just sort of do the propagation of constraint or of these symbolic values, like multiplying alpha by 5, you get 5 alpha. But then, if you ever hit a control flow statement that involves symbolic values, like the if statement we had over there on the right, then we're going to send a query to the SAT solver. And the query for them is called a path constraint, or a path condition. And this goes to this STP solver, and the solver is going to reply back, as we saw in the example with Z3. Either it's going to give us back an actual assignment and says, that's satisfiable, you can do that. Or it'll say unsatisfiable, like the answer we saw in the example on the projector where it said no solution. Or it just might time out. Well, either STP times out or this process times out and says, I give up, I don't want to wait anymore. And that's sort of the main plan. And if we ever have control flow that branches and both cases are possible, then the process is actually going to fork and create another copy of the process. And the idea there is that we'll now have 2 versions of this process in existence, and we can explore both branches and see what happens if we execute one way or the other. And this is the plan for exploring different execution paths. And then there's some kind of a scheduler behind the scenes that sits here as another process, and all the processes of the application that are running sort of talk to it behind the scenes to decide who gets to run next. Because there might be a whole bunch of processes that you forked off, and the scheduler decides who should get priority and who should wait a little bit if there's a large number of paths to explore. Does this make sense? That's sort of, I think, the physical plan of what happens when you're running something through exe. Questions about that? Good. All right. So let's look at an example to see how exe might execute this. So we might have some code that looks like this. Let's say we're going to have two values, x and y. We're going to read their values from the input, from potentially an adversary. And then we're going to do a couple of if statements. So if x is greater than y, then we're going to assign x equals y. And then if x is less than y, we're going to let x be x plus 1. And then we'll have an assertion. If x plus y is equal to 7, then error. Not a maybe super interesting program, but it sort of illustrates. It's kind of annoying to figure out exactly can you get to 7, especially when x and y are changing under the covers here. Like here, we might start out with two values, but then x actually is the same as y in this path, and then maybe it hits this. It's kind of a complicated, annoyingly program to reason about. But symbolic execution is going to save us. It's going to give us a very clear plan for how to reason about this. So let me number the lines of code here so that we can refer to them. 6, 7. So with symbolic execution, we're going to try to explore all the different paths along which this piece of code might run, and hopefully see if we can trigger that error statement at the bottom there. Make sense as a goal? All right. So let's erase some boards and start simulating what exe would do with this program. So when we start out, I guess we're going to talk about running different lines of code, and we'll keep track of what's in x and y, and we'll keep track of the path condition as well. So initially, when we start out on line 1, we're going to read x and y from the adversary. So we'll let them be alpha and beta, some symbolic value. And the path condition so far isn't constrained. We haven't taken any symbolic branches yet. So the path condition is just true. It's always reachable. It's always possible to get to this point in the code. Then we're going to actually hit line 2, which tries to do an if statement. So it's going to check if x is greater than y. So what does it mean to check if x is greater than y? Well, here we're going to have x be alpha and y is beta. So now we're doing an if statement on some symbolic values. So we need to ask our stat solver if that's even possible. Can we actually go down that if statement, or do we have to take the else branch and not take the if statement? So for that, we might actually have to ask Z3. Might actually need it's probably locked up again. Oh, no, great. Still unlocked. So here we go. So let's try to simulate this piece of code as if we're using a stat solver behind the scenes. So I'll cook up some new values. So I'll have my a. I'll cook up a new a. And here I want to use a bit vector because these are not integers. They're fixed length integers. So, sorry. A is a Z3 bit vector called A, and let's do an 8-bit value. It'll be easier to reason about them. And we'll also have a beta called B, and that's also going to be an 8-bit thing. So now let's try to solve. Can we have A greater than B? Presumably the answer is yes, and I don't know. So like here are some values. It doesn't really matter super what they are, but for whatever reason it picked 129 and 128. We're actually not going to use those values yet. We don't actually care about the concrete values. All we care about is that it's possible to go down that if statement. So we're going to add that to our path condition. So alpha is greater than beta for us here in the path condition. And we'll continue on to line 3. So on line 3, we're going to set x equals y. So x is what y used to be. So now we'll have beta and beta here. The path condition is still the same. Alpha greater than beta. Now we get to line 4. Now we still have beta and beta. We're going to ask Z3, is it possible to go down that if statement now? And presumably that's going to be fairly simple. Can we have x less than y? X is beta. Y is beta. No solution. We don't have to run down that if statement if our path condition happens to be alpha greater than beta. So we skip line 5. Is this making sense? All right. So then now we get to line 6, and here we have beta and beta in x and y. The question is x plus y equals 7. So x is beta, y is beta. Can it be equal to 7? So beta plus beta equals 7. No solution. Great. So we don't branch. So we keep the path condition, and we're done with the program. So this execution path terminated. We didn't hit the error path, but there's probably more things to consider. So let's try to understand what we did. So we started with line 1. Then we ran to line 2. Line 2 had an if statement, so we actually took one of the branches. So this is the branch with alpha less than beta. Then we started running line 3. I'm just sort of reconstructing that execution path in a kind of a graph so that we can understand what other paths we need to hit. And then after line 3, we started running line 4. Then it couldn't get to line 5, so we ran line 6, and we didn't run the error case. We're done. But there was another branch here that we didn't consider yet. So that's another execution path that exe needs to consider. So actually, when we started considering line 2 here, exe would have forked off a process. And now we need to come back and see if there's anything else to consider on the other side of that if statement. That make sense? Questions so far? All right, so let's look at another execution path, another process that exe forked off. So what that process is we're sitting on line 2 because that's where we forked. And we need to ask the SAT solver if we can actually go the other way as well. So on line 2, we're now sitting with alpha and beta in our x and y variables. But now the path condition we want to consider is, could it be the case that alpha is less than or equal to beta, sort of the opposite of what we considered. So we can, of course, ask the SAT solver. That should be hopefully pretty easy. So less than or equal to beta. Yeah, sure, no problem. So we can continue running down that branch, meaning we skip the if statement. Now we get to 4. We still have alpha and beta. Now we need to ask, can we go down that if statement while this path condition holds? So if you remember up there, with that path condition, we couldn't take the second if statement. But with this path condition, maybe it's possible. So let's check. So here's our constraint, a alpha less than or equal to beta, and the if statement is x less than y. X is alpha less than y. Yeah, that's possible. Could be 120 and 128. You know, again, the values don't matter for now. All we're going to do is proceed down here, and the statement is x equals x plus 1. So x is now alpha plus 1. This is beta. Our path condition is alpha less than or equal to beta. And also alpha less than beta, because we took that if statement. Maybe there's another path to explore. So I guess we should write this down here. So we got to 4. Then we took the branch where we actually went inside the if statement, 5. There's maybe a dangling branch here that we don't take. We'll get to that later. And now we're executing further. So on line 5, we're here. 6, we're at alpha plus 1, beta, alpha less than or equal to beta, and alpha less than beta. And now we need to figure out, can we go down into that if statement that is going to cause a panic? Well, we can just ask Z3. The constraint is x plus y equals 7. X is alpha plus 1 plus y, which is beta, equals 7. Well, is it possible? Yeah. Turns out 127 and 135 are an answer. It's a little bit surprising. We'll get to why that works in a second. But now, yeah, maybe we'll get to this point, and alpha less than or equal to beta, and alpha less than beta, and alpha plus 1 plus beta is equal to 7. So what the hell happened? How is this true? Like, yes, it satisfies a less than b and a less than or equal to b. Why is a plus 1 plus b equals 7? Is Z3 broken? Or why does this work out? Yeah. Yeah, so we said these are 8-bit values. That's, I guess, when I created a and b, I told Z3 these are 8-bit integers. So in fact, if I add up 127 plus 1 plus 135, I get 263. So if 263 minus 256, that's exactly 7. So it like actually, Z3 computed a integer overflow for us that gets us the right answer. But I was like really cool here because we didn't have to think of integer overflows at all. Z3 has a complete plan of everything that's possible with fixed width integers. And it'll just cook this up for us. We don't have to think carefully about integer overflow cases or whatnot. We could have also probably synthesized some value that doesn't involve overflow, I imagine. But for whatever reason, Z3 just picked these values. And if I made A and B be 32-bit values, it'll probably also synthesize a 32-bit overflow. Let's try this. I'm curious. Let's say A was a 32-bit value, and B was also a 32-bit value. We can ask Z3 the same question. And yeah, like here's some crazy large numbers that, if added up, plus 1 are equal to 7 with an overflow. And they satisfy all other constraints too. So the, I guess, really important thing is, if you were to give these inputs to the real code, it would also get 7. So Z3 is correctly modeling how your machine is going to run. And even if you don't think about overflows, it will. Make sense? Questions? I guess, yeah, maybe I'm being a little bit sloppy here in terms of, yeah, so like it was true, but then we had to consider 2 branches, so then we went to set this to that. You're right, maybe what I should have written here, let me come back to it, is say, well, it used to be true, and then we switched to that on the if statement, and then in the other path, we similarly started with true, but then we added this condition because of the if statement, and then on line 4, we started with, line 4 is indeed the if statement. Here I should have said, yeah, it used to be alpha less than or equal to beta, and then we switched to alpha less than or equal to beta and alpha less than beta, and then we continue, so just for consistency, yeah. So, yeah, sorry for the slight sloppiness there. Yeah.
Could it just theoretically have chosen like A equals 2, B equals 4?
Yeah, absolutely, yeah. And it's got some random generator inside of it, actually, to de-randomize some of its heuristics, and yeah, absolutely, yeah. So that could have been another answer. So the one place, I should say, that the concrete value that Z3 tells us is going to matter is when we actually finally hit the error here. So on line 7, we actually run it, we actually hit the error. And here, in order to tell the user, tell the developer, look, there's a bug. This is probably a confusing line to tell the developer, but the cool thing is we can ask Z3, just tell us what the inputs should be. And then we can tell the developer, hey, run your code, type in those numbers, you're going to crash. No, nothing else matters. It's like a really satisfying property of exe and symbolic execution in general is that even though the machinery is super complicated and, maybe there's bugs in Z3 even, who knows? At the end of the day, you can just check it. You can run Z3. Z3 actually itself, when it gets to a bug, it gets a concrete input, and then it tries to run the real program on that input. If it crashes or hits whatever the bug definition was, it'll report it to the developer. If it doesn't crash, I don't know, something went wrong with exe, or who knows, there's some randomness, non-determinism, whatever. Exe will just ignore that bug. Even though maybe there was bug, who knows. But it's going to be very conservative about reporting bugs because it can provide extremely concrete examples of how to trigger the bug to the developer. And then the developer can just debug this. Like, they don't have to use Z3 at all, or exe, or any of this stuff. Just like, type this in and try to figure out how the hell those 2 numbers cause it to crash. It's like a very well-defined problem at that point. Question?
On the path diagram, the first would be A for alpha greater than beta.
Yeah, so maybe just to fill out this diagram over here. So here we kept going. So it was alpha less than beta. And once we hit alpha less than beta, and I guess we didn't branch in the other case. It was impossible, so maybe it doesn't get added to the path condition. Here, it's alpha greater or equal to beta. And then here, there's maybe 2 cases. One, on line 4, we do actually finally branch. So that's alpha less than or equal to beta and alpha less than beta. We can simplify, but exe doesn't necessarily do that. And then here is another possibility, which is alpha less than or equal to beta and not the other alpha less than beta. So that's also probably possible, although it doesn't end up leading to an interesting bug. But there are some more paths that exe could explore over here. And then I guess, yeah, we could fill out the rest of this diagram here. I'm sorry? Yeah. Could they be flipped? Yeah, it might be that I flipped something here. Let's try to understand. Yes, I do apologize. every single inequality here is wrong. Thanks for catching that. Greater or equal to, greater than, well, at this point, I'm just making it worse, so I'll stop. So why did I initialize them as bit vectors instead of ints? That's a good question. So one reason is that in the real execution environment, they're really bit vectors. They're not ints. So what an int is in a SAT solver is a mathematical integer that has no bound. 2 to the 100 is a possible integer value in a SAT solver. And that's not how C programs really run. I used it initially just to illustrate some examples of arithmetic in a SAT solver. But if our goal is to reason about how a program is going to run with fixed width integers, then we should use fixed width integers in the SAT solver. On the other hand, if you're reasoning about a Haskell program that's running on arbitrary unbounded integers, you can use ints to reason about what it's going to do because Haskell is at least trying to implement those same unbounded integers. Question? How does it perform on sort of a real program? Yeah, good question. So how does this stuff actually scale up? I mean, what's going to get in our way here? So branching is potentially problematic, and branching in particular that leads to many paths. So if there's many paths, that's just going to be costly no matter what, because Z3 or EXE doesn't really have a great plan for dealing with a large number of paths. It just needs to explore them one at a time because it forks off and then we got to explore it. So this turns out to be a pretty serious challenge in general with bug finding, is that if there's many different inputs that cause your program to execute in different ways and branch different ways, you might have to think about all of them. And that's tricky to deal with this. One possibility that this paper doesn't really consider, but subsequent work looked at, is the possibility, okay, maybe one saving grace is maybe we can merge them. So maybe we can fork a bunch of things, but eventually those if statements could converge. Like suppose this was a piece of code and then there was something else down here going on. Well, after line 7, maybe we don't actually care that there were like 4 to 5 different paths that got us to line 8. Maybe we want to merge them all back and start from scratch from a single symbolic state. Now, in order to merge symbolic states, all these forked processes, you have to sort of recombine them all into a single version of memory. So here it was very nice that we could describe, X has the value alpha and Y has the value beta or alpha plus 1, whatever. But if we merge all these states, then the value of X is going to be kind of weird. Like, suppose actually, what happens if we want to merge the state of the program at line 6? Well, so the nice thing is Y is always beta if we want to merge these two states. But X is either alpha plus 1 or beta. So if we want to merge these states, the symbolic value of X is going to be, if alpha less than or equal to beta, then it's alpha plus 1. Otherwise, it's beta. That's going to be the symbolic expression of what X is. And that's sort of the downside of merging, which is that you get much more complicated symbolic expressions for the values of variables that just diverge on the two paths. So a lot of the tricks that go into making merging effective is heuristics for deciding when is it worth merging. That's going to give us reasonably nice symbolic values or expressions. And when is merging just a bad idea and you should have just considered the two states separately and you don't actually save much by combining them together. So that's certainly one limitation of symbolic execution. You can only sort of consider so many paths. There are some merging tricks, but sometimes works. I should say, like, people have pushed symbolic execution extremely far, much further than what EXE, the paper, talks about. This is one of the first papers that did symbolic execution, which is why we're reading it. Describes the idea. But in terms of how far you can actually push this, there are some nice systems. I mentioned there's a system called S2E. You can actually Google it. That can actually run a whole virtual machine, QEMU, in a symbolic execution environment. And then you can find bugs in the Linux kernel just by running a whole VM with symbolic packets, for example, as inputs. Well, that's really cool. And they have all kinds of heuristics and tricks and merging to make this fly. So suppose you have a program that doesn't branch so much. If you don't have that crazy number of paths, is it going to work well? Are there other pitfalls for how much this is going to kill you? I guess the other one downside is maybe the SAT solver. can solve something. So if the SAT solver times out, for example, if we have like a SHA-1 implementation, we say, oh, SHA-1 is equal to the following string. The SAT solver isn't going to, invert SHA-1 for us all of a sudden. But what do we do when the SAT solver times out? So pretty much inevitably what happens is the symbolic execution system is going to treat this as an unreachable bit of code. And pragmatically, the reason it makes sense to think of it as unreachable is because we cannot figure out how to construct an input that gets us there. Because at the end of the day, we're going to have to tell the developer, here's the thing you provide as input and get the code to run there. If we can't get the SAT solver to tell us what input to use to get us down that path, well, we're kind of stuck anyway. So as a result, you're not going to, well, there's going to be another thing sort of limiting your scale in terms of how much you can push symbolic execution. It doesn't have to be like cryptographically hard problem like SHA-1. It could be just the overall complexity of these constraints. The constraints we've seen so far sort of fit on one screen, like one line even. But in real symbolic execution for something like a Linux kernel, you would have sort of pages and pages and pages of symbolic expressions that the SAT solver has to deal with. And even though they might not be terribly complicated like SHA-1, it's just going to struggle with a large number of interrelated constraints. So that's another reason why SAT solvers or symbolic execution systems might not scale to a large program, is maybe you just have complicated logic that ends up translating into a complicated set of constraints. And it's not going to be able to find inputs that trigger certain bugs. Make sense? Other questions? So in practice, many of these things actually translate into really a scheduling problem. So we looked a little bit at the scheduler in the composition of exe. The fact that SAT solvers time out, or that you have many branches, or SAT solver queries take a long time, all translates into the fact that you're going to have a lot of processes to consider, a lot of paths. You're not going to be able to get to all of them. So you have to make a judgment call, which ones are worth exploring. And if our goal is to find various security vulnerabilities, then what the paper proposes, and pretty much every symbolic execution system does in practice, is they prioritize inputs that tend to start running new code. Very much like we saw in the fuzzing systems. We want to look at the coverage, and we want to continue exploring inputs that seem to be hitting new code. Symbolic execution systems do the same thing. So the scheduler is going to look at all the different processes, or all the different paths that are currently active, and it's going to make a judgment call saying, this guy seems to be stuck in some kind of a loop and it's not running new code. Let's pause running it for a bit. Let's let the other guys run if they happen to be running new code. That's much more interesting. So the scheduler is going to do a prioritization job very much like coverage-guided fuzzing does in terms of choosing between an effectively unbounded set of things it could try. Make sense? How this works? All right. So let's talk about maybe one last aspect of exe that we can sort of fit in here, is their handling of arrays. That turns out to be somewhat tricky for them to deal with, and turns out to be kind of important for their goal of looking at memory bugs. So what do arrays look like in exe? So there's a couple of different situations you might run into. So one possibility is you might have a symbolic array that you dereference or index with a concrete value. So what this means is you have an array called S, and there's a bunch of elements in it, like S0, S1, and so on up to Sn. And when you index it with C, you're going to fish out one element of the array. This turns out to be actually pretty easy to do for exe, because at runtime, in any particular process that it's running, it knows what the value of C is. It's a constant, a concrete value like 3. So then if you index S of 3, well, you're going to get S subscript 3. That's the value. You just fish out that part of the symbolic S value. Another example might be that you have a concrete array and you index it with a symbolic offset. So here, the picture looks a little bit different. So you have a concrete array. Doesn't really matter what the values are. Maybe like 0, 1, 2, whatever, n. Could be just a sequential list of integers. But now the problem is that we're fishing out any one of the elements in the array. So this is, of course, assuming that we already checked for bounds. We need to check that, assert that S is between 0 and the length of the array. But assuming that it's in bounds, the value is kind of a complicated expression. It's something like, it could be C0, or it could be C1, or it might be C2, and so on. So what I mean here is like this is the value C1, C2, C3, Cn, if those are the elements of the array, and then they're sort of selected by this symbolic expression. So it's something like, if S is 0, then C0, else if S is 1, then C1, etc. And this is literally the symbolic expression that Z3 is going to be looking at. It's not a piece of code, it's a symbolic thing that goes maybe into one of these symbolic memory locations that we've been discussing. So it ends up generating pretty complicated symbolic expression for us to deal with. So if we have lots of examples where we use symbolic offsets into arrays, that's going to quickly sort of increase the size of the constraints we're dealing with and potentially make this thing run quite a bit slower. Make sense? So the most annoying thing for exe to deal with is dereferences of symbolic pointers. So if you just have, star s, where s is some arbitrary pointer, this is a pretty horrible thing for exe to deal with. One problem is that exe tries to maintain this model of memory where it thinks of different allocations as being different symbolic objects or different concrete objects. And when we dereference a particular array with a symbolic index, we're going to generate a symbolic expression that says, well, it could be any of the elements of the array. So that's at least somewhat bounded. But if we have a completely arbitrary symbolic pointer, then the symbolic value of this expression is going to be some horrible thing. That's not just the value of any one object, it's like every possible location in memory. So the value of star s is basically any memory location, depending on what s is. So that is such a ridiculously large expression that exe, I don't think even bothers generating that expression. They just don't handle star s at all in their implementation. They don't try to symbolically execute such dereferences. Would be prohibitively expensive. Make sense? Questions about array handling? Yeah? Yeah, okay, so the question is, well, what about code that really does this? So what exe tries hard to do is, in its translation step, it tries hard to somehow preserve information about which object a pointer is pointing to. So if Z3 knows that this is a pointer to a particular object, and it knows that it's been bounds checked, then it can generate a symbolic expression that gives you possible values of it being only possible values of that object that's pointing into. But if it's lost track of where this pointer was coming from, so if you converted a pointer to an int and then back to a pointer, then this translation step is going to lose track of where it was pointing to originally, and then it's not going to be able to bounds check it, and it's not going to be able to generate a concise symbolic expression for what the value of it is either. So they rely on certain kinds of code are not going to translate well. Yeah. Yeah, so the developer, like in the paper, they have examples. One is if you want to have Z3 consider some things as symbolic, you write, literally, make _ symbolic of pointer x in your code, and then Z3 runs, exe, when it sees this statement in your code, it'll assign a fresh alpha or beta or whatever to the contents of x. So that's how you specify what starts out being symbolic in your code. You just pepper it with these location statements in your code. And then if you want to put in a search for like finding a particular bug, you just write assert x. And then it's going to put an if statement saying if not x, then error or panic. Yeah, so that's a bunch of the translation that makes your C code execute over symbolic values. Because if you just, there's no way you just stick an alpha into a 32-bit register. So that translation step adds this table on the side that keeps track of which symbolic values are where, tracks the path condition, all this stuff. Make sense? All right. Okay, so that's all I had to tell you guys about symbolic execution. You'll learn much more about it in Lab 3, which has you add symbolic execution to Zubar. But that's a pretty cool bug finding technique. It's probably sort of second to fuzzing in terms of its effectiveness and how widely it's used, but it is pretty powerful and pretty widely used nonetheless. All right, so that's it for symbolic execution. See you guys on Thursday for the quiz.